So let's wait a couple of minutes and continue with this lecture. Can everybody hear me? Can you guys hear me?
Yes, we can.
Can you hear me? Yeah, okay, fine. So, all right, let's begin this. So for the agenda for today, we're going to try to wrap up variational autoencoders. But as part of the proceedings, we will actually recap some of the key points from last class. So here's the recap. We have seen how neural networks can perform classification or regression, like MLPs, CNNs, and RNNs. And we began discussing neural networks as generative models that can model the distribution of any data and generate data from this distribution. So we found that we define generative models, which are functional or computational models for the probability distribution of a given data, which are generically represented as parametric functions. And these actually encode a generative story for how the data were generated. And we also saw that these can be used to compute probabilities or to generate samples. And we saw some examples of generative models like Gaussians or Gaussian mixtures. And we saw that when we want to estimate generative models, then we estimate them. These are parametric models, and we estimate their parameters from observed data. The principle that we use to estimate them is the principle that whatever data you've got are very typical of the process that generated the data, that they're very boring. And so we try to find the parameters that maximize the log likelihood, the log probability of the data that you have observed, based on the principle that these data are very typical. And we went through a couple of quick examples where we showed how we could derive the probability distribution for, say, a multinomial distribution or a Gaussian, just using the maximum likelihood principle. But then we ran into this situation. In many situations, the observed data that you get might be missing information. For example, if you're trying to estimate a Gaussian distribution, but the data you get are of the kind that you see on the screen, where within each vector, some components are just not observed. The values are not zero, they're just not observed. So then how do you estimate the distribution from these data? Or in the case of a Gaussian mixture model. Now, in this case, it's not observations, components of the observation that are missing. What is missing are the steps in the process of generating the data. So when you generate data using a Gaussian mixture, it's a two-step process. In the first step, you select a Gaussian, and then you draw an observation from the Gaussian. But all we get to see are the observations. We don't see which Gaussian the data came from. And so now again, there's information missing. And in both cases, we found that the only thing we can make any assumptions about are, of course, the data that we have seen. So which is going to be the observed data. And so our maximum likelihood estimation can only maximize the probability of what we have observed and what we have not observed, and cannot do anything about what we have not observed. But because our data are incomplete, trying to compute the probability of what we have observed means that in these vectors, we can only compute the probabilities of these components, and you cannot consider the missing component, or over here, you cannot consider the Gaussian. And so this causes problems. We can estimate these models easily enough when our data are complete, but when the data are incomplete, they cannot be estimated. And so the issue was this, that you had these missing components of the data that had to be marginalized out in order to get the probability distribution of what you have observed. And so when you take the log likelihood, you end up with an integral or a summation inside the log where you are marginalizing out the missing components. And so this causes problems in our estimation. And so we defined something called, we saw that there's an algorithm. Why are these things? We could use the expectation maximization algorithm in this setting. And the EM algorithm proceeds as follows. We, in the EM algorithm, we try to complete the data. We know that if we have the complete data vectors over here, then it's very easy for us to estimate the Gaussian. But the problem is that we have these missing components, and these missing components make the estimation challenging. Or over here, for instance, if you knew the Gaussian index for each observation, it would be trivial to estimate the Gaussian mixture, but then these are missing. And so we cannot estimate it. So what we will try to fill in these values or fill in these values. And the EM algorithm is based on completing the data by filling in the missing components. The question was, how do you fill the missing components? So now, if I've got a vector, let's consider, for instance, a two-component vector, whose components are x and y. And consider the case where you're assuming that the distribution is Gaussian. Then the joint distribution of x and y is going to be Gaussian. It's going to be this bell-shaped curve, right? Now, if I've only observed x and I have not observed y, then for any given x, are the set of values of y unique? They are not. So what we will have to do is to slice this distribution at the value of x that we have observed. And when you slice the distribution, you're going to see this face. And this face is the probability of y given that x equals x0, right? And so when I want to consider, what do I fill in over here? It turns out that when I look at the specific value of x, there isn't a unique y for that x. It's y can take a whole range of values with different probabilities. And this distribution is dependent on x. If I slice the Gaussian at different places, I would get different faces for the distribution of y. And y could be any of these. We don't know which one. Similarly, if I were looking at the Gaussian mixture case, if I got an observation, and let's say the observation was out here. Now, if I just look at this observation, then I cannot tell you which Gaussian it came from. Here is the Gaussian mixture. All the Gaussians have been normalized by their prior probabilities, so their wall area sum to 1. And this observation O could have been generated by any of the three Gaussians because all three of them have non-zero probability of generating this observation. But then, if I ask myself, if I saw 1 million instances of this observation, how many of them would have come from the red Gaussian, how many from the green, and how many from the blue? And if I ask myself that question, then the probability that any of these instances of this observation comes from the red Gaussian is going to be this value here, which is proportional to the height over here at O, right? The probability that it came from the green Gaussian is going to be proportional to this height over here, which is right here, right? And the probability that it came from the blue Gaussian is going to be is going to be this term over here. So this is P of K given O. And so if I ask myself, how many of all of these, I've seen this O, I haven't seen the Gaussian index, but if I saw a large number of them, 1 million of them, how many of them would have come from the blue, how many from the green, and how many from the red? And the number that would have come from the blue is going to be, 1 million times P of from the blue given observation. The number that would have come from green is going to be 1 million times P of green given observation. And the number that would have come from red is going to be roughly equal to 1 million times P of red given observation. That's what I would expect to see. And so in EM, what we will do is this. Let me try to see if I can get a whiteboard. It's not showing the whiteboard, right? That's too bad. Okay. And now I don't know how to hide the whiteboard. Go away. This is unknown. Microsoft has just gone into a loop where it wants me to log in and won't let me not log in. This is unbelievable. Okay, spare me. Wait a second, folks. Hi. My laptop is thoroughly messed up. It has just decided that it's not going to show me the screen. I don't even know how to get to Zoom. Okay, let's stop sharing. Maybe someone of you can help me. Why is it asking me for a password? Okay. Oh no. It looks like I'm going to have to. I made the mistake of trying to use one of Microsoft's tools. Okay, so let me just try to draw this. Can you see my screen, guys?
Yes.
Yeah. So anyway, I'm just going to try to draw on this because clearly I cannot do anything else. This is a miserable operating system which nobody should use. Now, if I've got a incomplete vector with just this component missing, right? If I'm trying to fill this component, and I cannot be sure what the component is because it could be anything, if I've got, when I look at this Gaussian, it could be any of these values. So what I will do instead is, I was writing here, wasn't I? Oh, shit.
Try Zoom to hide or reset
Okay.
Zoom.
So maybe this is better. Okay, so what I will do here instead is, instead of just making one copy, I'm going to make many copies. And then in each copy, I'm going to fill in this value. I'm going to fill it in with one of these m's, which one of these values. And so when I fill it in with, say, this value over here, I'm going to fill it in with this frequency. If I'm filling in this value, I'm going to fill it in with this frequency. And so I'm going to make many copies and fill in the missing values with filling the missing entries with different values. And each value is going to occur many times. The frequency with which it occurs is going to be proportional to P of n given O. And so this box over here represents all of the copies of this guy with this missing entry filled in these many times. So now I can do this for every one of my incomplete vectors. And when I do this, now I have an entire collection of complete data. And then from this complete data, I can go ahead and I can use those complete data to estimate my Gaussian. The problem here is that in order to fill it in with the proportion P of n given O, I need to know P of n given O, which I don't have because I don't have this distribution. And so what we will do is we have an iterative algorithm, and within each iteration, we are going to use the current estimate of this distribution to compute P of n given O, and we make these clones. And then we estimate our statistics. The same thing would happen for the Gaussian mixture. So I don't know this color, so I'm going to make many copies of this vector. This is going to be a very large number, potentially infinite. And I'm going to keep filling in the colors, but the fraction of all of these instances that are filled with blue is going to be proportional to P of blue given observation. The fraction that are filled in with green are going to be proportional to P of green given observation. The fraction that are filled in with red are going to be proportional to P of red given observation. So although this is showing only one bar over here, this is actually a very large number of bars. And now that I have this completed data, I can go ahead and I can re-estimate the parameters of this distribution. So is this making sense to everybody so far? Questions? Yes, no? I'm not seeing any responses, guys, right? So I need to see a few people. Okay. Now, the point is, there are a couple of different situations. If I actually make infinite copies, it seems like it's an absurd thing to be doing when I make infinite copies. But in the situation where I make infinite copies in some models, that is actually going to simplify the math so that with the parameters of this expanded complete data set end up being computable with a closed form formula. And those are the formulae that we use when we estimate our GMMs or with or Gaussians from incomplete data. So that is one setting. But then there are other settings where you cannot fill in all infinite copies of this guy. And so what we will do is when we want to fill in this missing component, we will compute P of m given O, which is a probability distribution, and we will sample this distribution. And when you sample this distribution, you're going to get a certain number of samples. So you're not going to be looking at all infinite values over here. You're going to be sampling them. So maybe you get some samples here, some sample here, some sample here, some sample here, and some sample here. You will get more samples from more probable regions, fewer samples from less probable regions, and then you're going to explicitly fill in the missing values with the samples that you just drew. And so now we're going to make this completed data set using these samples that you got from the posterior probability distribution. And now you can go ahead and re-estimate the probability distribution using the samples. You could do this in both cases. So these are the two ways of completing the data before you re-estimate your parameters. So does that make sense? Yes, no? Guys, I expect you to respond. You slow me down, so respond. And if anybody has a doubt, speak up now. Right? Okay. So this is fine. This is the standard EM principle. I'm not going to throw math on it because we're going to be, the basic idea is that when you get data with missing components or missing structural elements, we complete the data by filling in these values in proportion to P of the posterior probability, and then use the completed data to go ahead and estimate our model. So that's EM. The other question that we came up with was principal component analysis. Now in PCA, here is the basic problem. You're given a set of centered data. We'll get to what centering means. And we want to find a subspace such that the projection of the data onto the subspace results in the lowest total squared error. Now, there's a lot packed into this one sentence, so I'm going to try to simplify it. First, what is the notion of a subspace? A subspace is the set of all vectors that can be composed as a linear combination of a set of basis vectors. So suppose I give you two vectors, W1 and W2, in any space. What is the subspace of that can be constructed through linear combinations of W1 and W2 going to be? What is its shape going to be? Is it going to be cubic? Is it going to be a plane? Is it going to be a line? What will it be? Anyone? It's just going to be a plane, right? So if I take any two vectors, the set of all possible vectors that I can just compose as some A times W1 plus B times W2, that is going to be a plane. Or if I take K vectors, that's going to become a K-dimensional hyperplane, right? That's what we mean by subspace. And the subspace always includes origin, because I can set A and B to 0, and that's going to be one of the vectors, right? So now, the same subspace can be composed by different sets of bases. Any set of linearly independent bases that lie within the subspace can be the basis. So if you look at this plane can be composed as a linear combination of W1 and W2. It can also be composed as a linear combination of W'1 and W'2, right? So within this plane, I can take any two odd vectors within the plane, and a linear combination of these two vectors will compose the entire plane. Basically, the plane is the surface within which those two vectors lie. If I give you two vectors, there's only one two-dimensional plane within which the vectors lie. And so within any plane, I can randomly choose, I can get essentially infinite combinations of pairs of vectors. And any of these, if they're different, linearly independent, they can compose the plane. So that means that the same subspace, the subspace is unique, the bases are not unique. You can construct it, the same subspace with many different bases. Now, mathematically, if I give you some bases, if I give you some basis vectors, I can pack them into a matrix. And so any linear combination AW1 plus BW2 can be written as W times AB, because W is W1 times W2. I can write this as a position vector Z. So any vector in the plane is going to have the form WZ. This is just the math, okay? And now, what is the notion of projection? I have defined a plane. A plane is the set of all vectors that can be composed as a linear combinations of the bases that you chose. Now, suppose I have some vector, like this guy over here, some point in the space. There is a point on the plane which is closest to it. So if I compute the Euclidean distance of every point on this plane from this guy, each of the points is going to be some distance from this vector. That distance is going to be the length of this line. And there is this one guy on the plane directly beneath it, which is the closest point on the plane. So this point on the plane, which is the closest to the point that we started off with, that is the projection of this point on the plane. So mathematically, remember, if I've got my plane is expressed in terms of the basis W, right? So I want to find the position vector Z prime on the plane such that W times Z prime is closest to V. So finding the projection of a point on the plane is the same as finding the position vector that minimizes the error between the point and the projection. Basically, that minimizes the length of this line. So, and when we do that, this line over here is the error between the point and its projection. If you approximate the point by this projection on the plane, and that is always going to be orthogonal to the plane. So also, when we set this up, I'm trying to approximate, V equals some WZ. And there's a closed form solution for this. It's simply going to be Z equals the pseudo inverse of W times V. So that is the projection. Now, any questions on this, the definition of a projection? Any questions, guys? Yes, no? Is this clear, what a projection means?
Yes, it's clear.
All right, so fine. Now let's continue. Now, there's the notion of finding a best subspace. Given a set of data vectors, I want to find the subspace such that when I project every data point onto that subspace. So these red and blue points are my vectors, and the gray shadows underneath them or above them, they are their projections, right? So this one's projected here and so forth. Now, I want to find the subspace such that the total length, squared length of the error that you get when you project every data point onto the subspace and approximate it by the projection on the subspace. I want to find the subspace such that the total error is minimized. So basically, if I have a collection of data points, then each data point, when projected onto the subspace, is going to be some W times Zi, where this is the closest guy to this one, right? So this is the closest point to V. Even though you get to the closest point on W, there's still going to be an error. So this is the projection error for the I and squared projection error. And you're summing that over the entire data set, and you want to find the basis such that this error is minimum. Now, if this is not very clear, I can write it out like so. If I put all of my data vectors into a matrix V, so this is just V is just a stacking of all of my data vectors, and Z is a stacking of all of their position vectors. Then I'm trying to find the position vectors. I'm trying to find the bases and the position vectors on this basis for each of my data points, such that the squared error between my data matrix and its projection on the subspace is minimized. Again, this math may not make a lot of sense, so we'll see this with pictures. Let's say I've got this collection of data points. Now, this is in 2D, right? So I want to find a one-dimensional subspace that best represents this data. What is a one-dimensional subspace? Anyone? What is a one-dimensional subspace? It's just a line through origin, right? So now, here are 4 different 1D subspaces. Now, in this guy, this is one. When I check this one, these black lines, so the red dots represent the projection of the blue dots on the subspace. And the lines show the length of the error when you approximate the blue dot by the corresponding projection on the subspace. So if you look at these 4 pictures, 1, 2, 3, 4, which of these subspaces gives you the lowest error due to approximating the data points by the projection? So when I replace the blue dots by the red dots, which one gives you the lowest error? 4, right? So this guy is probably the closest one to your principal subspace. And so what principle finding the best subspace is, this was, oh my good God, this was supposed to be the animation that we saw in the last class, where you essentially scan through all possible subspaces and search through every possible subspace until you find the subspace that minimizes the squared error. So I can draw, no, so something is wrong with my draw board. It's something is wrong with my laptop because it's my tablet and the keyboard has disappeared. I've got to attach a keyboard. Let me try. When I attach a keyboard, the whole thing messes up and I can no longer draw. Okay. Escape key. No, it's not working. So this is just one of the problems with Microsoft. It's been asking me to reboot it for 3 days. Anyways. So the problem of finding the best subspace is the problem of finding the subspace such that this total error, squared error for your training data is minimized. And so you want to search through all the subspaces to find the one with the minimum projection error. But then before that, there's another thing that came up in the quiz, the question of centering. I have this collection of blue data points, and I'm showing you two different lines. One is this blue one, which is a proper subspace, and the other one is a red one, which is not really a subspace because it's not going to the origin, but it has the right general direction. Now, if I were to project everything onto one of these lines and represent and approximate them by their projection on the line and use that as a representation, which of these two gives you the better representation in your opinion? The red, right? But then you can't really just solve for the red using this math we had over here, because this math assumes that this is a subspace which goes through the origin. So what we will do instead is perform a simple trick. We want to get this guy, but how do you compute it? We're going to take this entire data set and slide it into the origin. So which means that we take the center of this data set and move it to the origin so that the entire data set is now centered. And now that it's centered, I can use the same trick that I used to find the best subspace, and that's going to give me the red line. It's going to give me the correct direction. So I can shift the center of the data by shifting the mean to the origin and find the principal subspace for the centered data. And so these were the two representations that we got. When you don't center the data and just work directly with the raw data, this would have been the best subspace you could find. This red line would obviously give you much greater error, correct? So whereas if you center the data, the best subspace that you're going to find is the red line. Now, when you use the uncentered data, this is going to minimize the total squared error over here. And it's going to actually, what this does is it retains most of the squared magnitude of the vectors because all of these vectors now end up over here. So the lengths of the vectors are mostly retained. And you arrange them on some subspace in a manner that retains most of the length of the vector. Now over here, if I projected the data onto this line, will the length of the vectors be retained? Anyone? Will the length of the vectors be retained in the second case? No, right? Because this vector over here is going to be represented by this one, whereas the original vector was here, right? Out here. So there's no relationship between the original vector and its projection. So what the second projection does is it retains most of the variance, the information in the data, but it loses information about the length, the energy in the data. The first one retains most of the information about the length, but then it's not the more optimal representation. So this guy is the Cardinal transform. This is the principal component analysis. And we like this one because variance is related to information. Statistically, that makes more sense if you want to make inference.
Professor,
I'm going to assume that the data are always centered in today's discussion because that eliminates the distinction between KLT and PCA. So we're going to assume, and anytime you get a data set, you can just subtract the mean and center it, and it's all going to work. So this is fine, right? So now, when I want to find the principal subspace, I'm basically trying to find the W and the Z, which is to say I want to find the basis for the subspace and the position of each vector in my data set on that subspace such that this combination, the error between so this represents the projections of my entire data, right? Entire data. And so I want to find the bases and the Z such that the squared projection error for the entire data set is minimized. Is this making sense? So what do I mean by retains length? Let's look at this one here. So when over here, this is the length of the vector. These are the lengths of the vectors, right? And so when you look at their projections, the lengths of these projections are approximately the same as the lengths of the original vectors. If you look at the lengths of the projections of the shifted copies, there's no information about how long the original vector was.
But in the first case, it is also taking care of the variance between the data, right?
No, it's not. It's going to capture some of the variance, but really, right? This is not right. These two are completely unrelated representations. There is no guarantee that you're going to get the direction. For example, if I have, so let's say I have data of this kind, okay, and I find my KLT, the optimal projection is going to be this, correct?
Mm-hmm.
Right through the center. All of the data points are going to end up here. How much variance did you get?
0.
Exactly, right? So can you add the mean back after performing PCA? If you're interested in the variance, yeah, but if you add the mean back, it is not, so there's a difference between a model of this kind, summation AI WI, and summation AI WI plus B. So this has a bias. This does not. This is a definition of a subspace. This is not a subspace because it's affine, right?
Mm-hmm. Okay.
So
Right.
you can actually have a learned bias term into the subspace, and if you actually use a learned bias term, the optimal learned bias term will end up being the mean of the data. So if you use this model, this is going to give you PCA. This is going to give you KLT. This is to answer Justin,
Got it. Thank you.
right? Justin, did that answer you?
Yeah, that does answer.
Okay. So now here is this problem. This is a quadratic problem, but what is it quadratic in? It's quadratic in WZ, correct? If I write WZ equals V hat, then you're trying to you're trying to minimize V minus V hat squared. And this is quadratic in V hat. Quadratic functions have this shape, they have a unique minimum, correct? So you're going to get a unique answer for WZ, which means you're going to get a unique answer for the projections of the data because WZ represent the projections. So this one will correctly give you all the gray shadows, but will it give you a unique set of bases? Anyone? Will this give you a unique set of bases? It won't, right? All I got was WZ. So I can take any W1 Z1 equals, W1 times B inverse Z1, and they'll all be the same. Basically, once you find the subspace, you can find any two bases on these guys, and you'll get corresponding any set of bases on the space, and you will get the corresponding position vector. So the subspace is unique. The bases that you find are not unique when I'm performing PCA. Still, if I want to find a solution, I can try to solve for this just using quadratics, which will give me WZ. And then from my WZ, I can try to extract some W and some Z. You'll find the V hat. And from V hat, you can try to extract some W and some Z, and it's not going to be unique. You can have an iterative solution where I'll say initialize my W. And then once I initialize my W, this becomes quadratic in Z because the W is fixed. And so now I can get a unique solution for Z. This minimizes the squared error. Then I fix my Z. And now I can estimate my W. And because the Z is fixed, it's quadratic in W. And then I can go back and estimate my W. I can iterate this process. And eventually I'm going to find an optimal, I'm going to end up with a solution where because at each step, the error keeps going down, and because the overall error is quadratic, I'll finally end up at this minimum error solution. I will find the correct subspace, but then depending on how I initialize this iteration, I'll get different bases, right? So now, nevertheless, what is this process? if you go back and look at this solution over here, I have z equals w plus v, w equals vz plus, correct? So at each step, there's just a multiplicative term. In other words, that entire process of going from x to, so I've changed my notation and gone from v to x. And I didn't have time to fix my slides, so just stay with this. So this business of going from x to this intermediate representation z, which is the position vector on the subspace, and then going back from z to my x hat, which is my best reconstruction. This is a linear autoencoder. This is the encoder, this is the decoder, and this is just a linear autoencoder. So is everybody seeing this? Yes or no? Guys?
Yes. Yes.
Okay, and in fact, these guys don't even need to be pseudo inverses of one another. I could use any two matrices over here. And if I learn this to minimize the error between x and x hat, I'm guaranteed, because the reconstruction is based on W, I'm guaranteed that this thing is going to be a set of bases in the principal subspace. But that's just besides the point. What is this solution actually doing? The way we are thinking about it, suppose somebody gave me a position vector for each x. So I have my data point x, and suppose somebody gave me not the projection, but the position vector in terms of my bases. Then, if I have the position vectors for all of these guys, I can find the bases for my subspace trivially, right? We just know that the bases is going to be just x times the pseudo inverse of z, correct? So if I had this position vector on for each of my vectors, finding the principal subspace is going to be trivial. The problem is we don't have this guy. So what the iterative solution is doing is that it's guessing the initial subspace, then using the initial subspace to complete the data. It's estimating the z's. The data we had were incomplete. The z was not available. So it's completing the data by estimating the z's, and then using the completed data to go back and re-estimate the subspace. And it's flipping back and forth between these. What does this look like? Where you complete the data and estimate your model, use the estimated model to go back and complete your data. What was that process?
EM.
This was just EM, right? But then EM was designed for statistical models. What is the generative model behind this process? It's not immediately obvious. So let's go back and look at it slightly differently. We know that this one does not have a unique answer, uniqueness. We like to get unique answers, so we can impose constraints. One constraint I can impose is on the weights matrix W. I can say that my bases must all be unit length and they must be at 90 degrees to one another. If I impose this constraint, this is like saying that the inner product between my basis matrix is the identity matrix, or is going to be the outer product. This should have been W transpose equals R. Anyway, and when we impose this constraint, then those of you who have gone through principal component analysis, you're familiar with the eigenvalue solution that you get for PCA. That is the outcome of this constraint on W. But then instead of constraining W, there's an alternate option. You could either constrain this guy or you can constrain Z, right? I can instead impose a constraint on Z and say that the position vectors on Z must have a Gaussian distribution. And not just a Gaussian distribution, but a Gaussian distribution with, say, unit zero mean identity variance. And when I do that, that's the equivalent of saying that, you know, if Z is a zero mean unit variance Gaussian, WZ is also going to be Gaussian. That's like saying I'm going to find the position vectors are scattered in a Gaussian manner. And if I impose that constraint, that too is going to give me a unique solution. So strictly speaking, what this is doing is, in this case, the W's are being required to be orthonormal. Over here, the Z's are being required to be statistically orthonormal. The two are basically the same model to within a scaling factor. And so the two solutions, whether I'm going to be imposing a constraint on W, which gives you a standard PCA, or on Z, which gives you this modified version, they have the same generative story. And so let's look at the generative story. Now remember, in PCA, when you go backwards, you are replacing every point by its projection on the space, right? So that is the going backwards from the point to its projection. The forward story is like saying, I'm taking a step to this projection and then taking a perpendicular step off the space to construct my point. So the generative story goes backward. It's like saying, I'm going to take a step on the space, and then I'm going to take a perpendicular step off the space. And that's how I construct my data. And specifically, when you assume that the position vectors are Gaussian distributed, then you're saying that you're taking a step on the space whose distribution is Gaussian. I'm drawing from a Gaussian distribution on the plane, not off the plane. So I'm drawing from a Gaussian distribution on the plane to take a preliminary step, and then taking a step perpendicular to the plane to generate my data. That would be my generative story behind PCA. This is regardless of where you impose the constraint, whether it's on W or whether it's on Z. Is this making sense, guys? As a generative story, when I flip it around. Yeah, okay. And I'd like to see a few more yeses. There are just 3. Any questions? Because I just assumed that you got it. No questions. Okay. Fine. So then when I assume that Z comes from a 0 mean unit variance. I need a piece of paper. Do I have one? Yeah. So when I assume that Z comes from a 0 mean unit variance Gaussian, what I'm really, the model here is this, that I'm first drawing, I've replaced my W with A over here because that's what we use for autoencoders, that I'm drawing my Z from a 0 mean unit variance Gaussian. Then I'm transforming my Z through this A. Here the A are the bases. My notation keeps changing, okay? And then you're going to get an X hat. So this is like saying, when Z is a 0 mean unit variance Gaussian, then AZ is going to also be 0 mean, but the variance is going to be AA transpose, right? So it's going to be some ellipsoidal distribution on the plane. So this stage over here is like saying, I am taking a Gaussian step on the plane. And then once you do that, I'm adding a noise, and I'm saying that the noise of the plane is perpendicular to the plane, but the noise is also drawn from a Gaussian distribution. And so the entire generative model here is, I take a Gaussian step on the plane, and I take a Gaussian step perpendicular to the plane to generate my data. And because the noise over here is always perpendicular to the plane, it's low rank and orthogonal to the principal subspace. This is the generative data behind PCA when I impose the constraint on Z. Is that making sense? Yes or no, guys?
Professor?
Yeah.
I have a question. Is that, can you explain the last point, what it means that the covariance of Gaussian is low rank and orthogonal? Like, what does it mean? Covariance of...
So because the noise is only allowed to be orthogonal to the plane, correct? Right?
Yeah, correct.
So if I look at the distribution of the noise is only going to be in this direction. There will be no distribution in the other directions, correct?
Yeah.
So when I look at the covariance matrix C and I look at its determinant is going to be 0. If I look at the eigenvalues of the covariance matrix, there's going to be only one non-zero eigenvalue in this case, because there's only one direction of variation for the Gaussian, for the noise.
Okay.
Right? So when I'm saying low rank, it basically says that the noise can only vary in one direction. And so, a different way of looking at the same model, I don't know if you can see my paper, is like saying I'm taking this small linear Gaussian, which is my Z. So this is my distribution for Z. This is the plane on which lives on, and it's going to be, let me see if I can adjust the camera so you can see my paper. So this is going to be my distribution for Z. And when it passes through this linear transform, it sort of maybe rotates it, stretches it, and shears it, but it's still going to remain a plane, except what went in as a circle. If I drew a perfect circle on this paper going in, when it comes out, because I've rotated it and stretched it and warped it and sheared it, it's no longer going to be a circle, it's going to be an ellipse. So I can say that AZ stretches and rotates the k-dimensional planar space of Z into a k-dimensional planar subspace in the data space. When it goes in, so if I'm working, if Z is two-dimensional and A is if I'm in three-dimensional space, and if my principal subspace has only two bases, then Z has only two components, right? And so Z is just going to be a two-dimensional space. It's just going to be a piece of paper. It doesn't even live in 3D. When I put it through A, that transformation takes this thing and puts it in three-dimensional space, in the full space after stretching and shearing it. And so this transformation takes a planar surface and puts it in 3D in my example after shearing and stretching it. And specifically, this Gaussian distribution on this planar surface is going to become some other distribution, also a Gaussian, but stretched and sheared in the higher dimensional space at this point. And then finally, I add some noise orthogonal to it. So the data occupies the entire space. So is this making sense, guys?
Yes.
This model. Okay, so that's what's happening, right? And so what is the probability distribution modeled by PCA? If Z goes in and it's Gaussian, then X hat, it's only a linear transform. It's going to be Gaussian. Then I'm adding some noise to it, and this noise is Gaussian. So the sum of two Gaussians is a Gaussian. And so PCA models a Gaussian probability distribution. Specifically, the distribution of the data that it's assuming is zero mean, whose variance is AA transpose plus D, where D is the variance of the noise, and A is the transformation that transforms the standard Z. Okay, this is, and when you perform principal component analysis, you're actually performing ML estimation of PCA parameters. And if you just do standard maximum likelihood estimation of PCA parameters, you will end up with your standard PCA solutions. Now, for some reason I have, okay. So any questions so far? Any questions, guys? Was this clear? Yes or no? Please answer. Okay. So now, here is the problem. PCA's assumption is that the data all lie very close to this low dimensional surface in the higher dimensional space, and that the actual informative portion of the data is on the surface and the noise is orthogonal to the surface. That is the assumption that PCA makes. The data has a Gaussian distribution on the surface and the noise is orthogonal. So if you threw away the noise components and just retain everything that's on the surface, you're going to keep the important portions of the data. We're going to keep the noise-free version of the data. That is the assumption that PCA is making. Would this assumption be right? The problem is that noise is not always going to be orthogonal to your observation in real life. Noise can be in any direction, as we saw in the last class. I can look at random patterns of dots, and they can look like faces. They can look like bicycles. Noise can actually look like data. And so we can update the PCA model by a small change. Instead of always requiring that the noise must be at 90 degrees to the plane, I can say that the noise can be in any direction. The noise is uncorrelated, but now this D is full rank. So when I do this, the generative model becomes slightly different. The generative model is that I take a step on the plane, a Gaussian step on the plane, and then I take a Gaussian step off the plane, but the Gaussian step can be in any direction to generate my observation. And in real life scenarios, this is a more realistic assumption about your data, really, right? That noise can be in any direction. So when I make this simple modification over here, you get what is called the linear Gaussian model. And the linear Gaussian model also assumes that the probability distribution of the data are noisy, are Gaussian. You're taking this Gaussian, which is this low dimensional Gaussian in the low dimensional space. You put it through the transform, and it's going to end up, stretched and sheared in the higher dimensional space. And then you add full Gaussian noise to it. And so the linear Gaussian model also assumes that the data has a Gaussian distribution on a planar surface, very close to a planar surface in the higher dimensional space. Does this make sense? And can everybody see why this model is actually better than PCA? Yes or no? Anyone else question? I'd like to see a couple. Okay, I'd like to see a raised hands. Raise your hand if things have made sense so far. I'd like to see a bunch of raised hands before I continue. All right. Okay, 20 people. That's 1/6 of the class, 1/5 of the people here, but still that's better than nothing. Okay. Now, what kind of distribution that does the linear Gaussian model or PCA really model? It actually models a distribution where the data lies close to a linear surface and has a Gaussian distribution around it. So the linear Gaussian model is a generative model for Gaussian data, where the data are Gaussian, lying largely on a low dimensional surface with some Gaussian fuzz off the surface, with the assumption that the noise that's going off the principal surface is kind of uncorrelated. So this is the basic model for linear Gaussian models, and it does a very good case. We all use PCA. PCA works very well all by itself, even though its assumptions about the noise are unrealistic. If you took it one step further, it's going to work even better. And once again, the parameters of this model can now be learned using maximum likelihood estimation, same as before, except that unlike PCA, you're not going to get a nice closed form solution. So once again, when you have linear Gaussian models, if you had the position vector for every vector, then it would be much easier for you to estimate the subspace and all the parameters of the model. So we do the same thing. We're going to use the same trick as before. We will initialize our subspace, use this updated linear Gaussian model to complete the data and make many clones of the data, and then re-estimate the parameters of the model using the completed data. And once again, when you complete the data, you can either complete the data in every possible way, all infinite ways, in which case you can't explicitly complete the data, but you will do this mathematically and the math should work out. But it's just easier to actually sample the probability of z given x and use the sample values of z given x to fill in the missing data. And now you can use this sampled data to go back and re-estimate your model parameters. That's your linear Gaussian model, okay? And so there's a lot of math over here that I'll skip. It's not really necessary. These are supposed to be hidden slides. But Microsoft isn't being friendly today. Anyway, so here's what we got. Linear Gaussian models are extensions of PCA, which specifically have this generative model for their data, where they model the distribution of the data as Gaussian, where most of the variation in the data lies on a linear manifold with some fuzz of the manifold. So they're excellent models for data whose distributions actually fit these assumptions, like this, something that has a scatter like this, or something of this kind, or something of this kind. This is in 3D. This is actually a data which is lying very close to a two-dimensional plane. So and a lot of real life data samples are actually like this. So they're really good models. But then what if you have data that looks like this? In this case, the data are still kind of Gaussian distributed and say have some fuzz off a surface, but the surface is not planar. So the linear Gaussian model assumed that the data had a Gaussian distribution somewhat distributed closely to a planar surface. But then if the data are Gaussian distributed but around a curved surface like this one, what would you do? How would you modify your model to deal with this kind of distribution? Does anybody want to guess?
Transform it into a linear subspace.
So
Transform it to a linear
closer to your
subspace.
mic?
Yeah, transform it to a linear subspace.
You can transform it through a non-linear function, right?
To a linear, yeah.
So what we did earlier was we took our Gaussian and transformed it through a linear function. Instead, I can make f of z a non-linear function. This becomes a non-linear Gaussian model. And so f of z now is a non-linear function that can take in a plane and fold it and produce a curved surface, a curved manifold, like the decoder of a non-linear autoencoder. The samples of z then are placed on this curved manifold, and the actual data are produced by adding noise samples to the manifold. So is the simple extension of your linear Gaussian model, where now instead of simply having a linear transform, we have a non-linear transform. So what does it do? There are two components to this NLGM. The first one is this nonlinear function, which takes this low-dimensional planar Gaussian and puts it through some transform and converts it to a surface in a higher dimensional space. Except the surface is now no longer planar. It warps it and creates a curved surface in the higher dimensional space. So it could take something of this kind and create a curved surface. And the data are still going to have the same kind of distribution over here. The distribution that the data will follow on the surface are going to roughly follow what went in. So if this is a continuous function, then regions close to the mean of this Gaussian are going to have high densities of data on the surface. This is not the probability distribution function. What you're seeing to the right is the surface, and the color is the probability distribution function. And so on this surface, basically you're saying that all of my data now lie on a surface of this kind. And because I started with a Gaussian, which had high probability right here, when I curve the surface, I'm going to find the highest density of data at this peak, right? The portion that came from the mean in the input space. And places which had low probability in the input space, the folded the folded version of it in the high dimensional space is also going to have low density of data. And so the density over here is going to be basically sort of correspond to the density in this input, but it doesn't have to be Gaussian anymore, because this could be stretching and warping the surface in non-linear ways. And then we will say, okay, once we've transformed this planar surface to this nonlinear curved surface, we are still going to add uncorrelated Gaussian noise to the output. And that is going to give me my final observations. So the final observations are obtained by adding uncorrelated full dimensional Gaussian noise to the samples. So is this clear to everybody? Yes or no? Raise your hands if this makes sense. The distribution of Z is going to be Gaussian, but after it's been put through the transform, because the function f could be stretching different portions of the space in different ways, right? So it's going to be a nonlinear transform. It won't be Gaussian. That makes sense, Jay?
Yeah. So it's going to be a nonlinear. It's going to be a non-Gaussian distribution plus a Gaussian noise.
So it's not going to be Gaussian on the curved surface.
Yeah, but the noise is still Gaussian.
The noise is still Gaussian. And what is the variance of the noise? At this point, all we know is that the noise itself is uncorrelated, right? And so the generating process, we'll get to that later, right? So here's the generating process. It draws samples from this isotropic Gaussian, puts it through this nonlinear transform and places it on this curved manifold. And then it adds uncorrelated noise, isotropic noise. So it doesn't have to be orthogonal to be through the surface. It could be anywhere. It adds uncorrelated noise to the data on the outside, on the surface, to produce your final observation. This is the generating process for the nonlinear Gaussian model. So, questions so far? None. Okay. So the thing is, this kind of process can model very complicated distributions that may be, viewed as lying close to a k-dimensional surface in the data space. Or, the linear is a special case of this one, right? So you could even be modeling distributions of this kind, which are, data lie very close to a helix. Because in that case, this function f should take our planar manifold and begin rolling it up into a helix, right? So, and the manifold over here, the local dimensionality of the manifold is going to be the same as the dimensionality of Z. Now, the key requirement in building this model, we need to know the dimensionality of this manifold, because that is going to be the dimensionality of Z. And then you need a function f that can transform this planar k-dimensional surface from the input to the desired curved k-dimensional surface in the output. So the design choice, you're going to have to select or guess the dimensionality of the manifold, which is the dimensionality of Z, and choosing the right function f that can model the shape of the manifold. And we will try to learn the shape of this manifold. And for this function is going to be a neural network. So now, how do we learn the NLGM? Guys, I'm going to go over today. I'm going to go shamelessly over because I blame my laptop. It wasted 10 minutes of my time. Please bear with me. Okay. So given a collection of data. So you've got a collection of data. What are the parameters we want to estimate? We want to estimate this nonlinear function, which folds this planar surface into the right shape. And then Gladys, here's the answer. We don't know what the covariance of the noise is. We only know that it's a diagonal covariance matrix because we're assuming it's uncorrelated noise. So the things we need to estimate for this model are the parameters of this function so that it captures the right shape, and the covariance of the noise itself. And we are going to use maximum likelihood estimate to learn these parameters. Everyone with me so far? It quickly gets more complicated from here. Okay, I will take 2 yeses as a yes, representing everybody in the class. Now, what is the probability that the NLGM models, right? First, if I give you the z for a given function, if I give you the z, then I'm giving you x hat. X hat is simply the function of z, correct? And then I'm adding a Gaussian noise with 0 mean. So if I'm giving you the z, the x hat is fixed because this is a deterministic computation. To that, I'm adding some noise. So if I give you the z, the probability distribution of x is still going to be a Gaussian. It's going to be the same Gaussian as this noise. The only thing that happens is that this mean is going to shift to f of z at the given z. So is this one making sense to you guys? Questions? Yes or no? Lower your hands and raise it again, right? This is making sense. Okay.
Why is the mean of the resulting Gaussian x not x hat?
Can you come closer to the mic? I think either you.
Sorry. Yeah.
Yeah.
So why is the mean of the resulting Gaussian not x rather than x hat?
So the mean is x hat, right? And x hat is f of z theta. Does it answer you?
But what does the x mean? So just before the fz. So and x semicolon. What does that x mean?
So I'm not sure. I didn't hear you clearly. Can you repeat that, please?
What does the x in the line that you draw the arrow to me? So that is a conditional probability, is it?
Correct. So I'm saying, suppose I give you the z, correct? What is the probability that I'm going to observe any given x? So that probability is the only variation, the only randomness comes through this guy, correct? X equals x hat plus e. X hat is a constant because z is given, so x hat is fixed. Implies p of x equals p of e, this e plus x hat, which is simply going to be a Gaussian with the mean going to 0 plus x hat and the variance retained. Does that make sense? Yes or no?
Wait, I'm still confused on the notation. Yeah, on the final notation.
Are you asking what the x is before the semicolon?
Yeah.
This is
So
saying
this
that the
is the
normal
variable
distribution.
and these are the parameters.
Yes.
Oh, okay, got it.
This is the random variable, this is the mean, this is the variance.
Yeah, I got it. Thank you.
Okay, so the standard notation is I'm doing x, semicolon, mean, variance. That's the notation I've been using. Okay. So now, given this, I will suppose, let's just first consider the situation where I have complete data. So what I mean by complete data is that for every x, I have the corresponding z. So we're seeing the entire process. In fact, it's not complete, but it's mostly complete. We are not seeing the specific e that we got. But for every x, I'm seeing the z that went into the process to generate the x. If I got the z for every x, then how can I estimate the model for the NLGM, the nonlinear Gaussian model? So that's easy. So this is the glass box process. which gives us, when in the glass box process, I'm assuming that I'm seeing the Z that generates every observation, and I'm seeing the observation. So I have a collection of observations and I got their Z's. And I'm going to try to estimate the model parameters of the model from this complete data, right? And when I do that, the probability for any particular instance is just given by this Gaussian. So given the complete data, all the observations and their corresponding Z values going in, then the log likelihood of the data is going to be the joint probability of P of X and Z. Actually, Z is given, so I just need to worry about the probability of X given Z, correct? And the probability of X given Z is just this Gaussian, which is given by this term here. This is my Gaussian, and the log of, so the log Gaussian is the log of this term, which becomes, you know, the log of minus half the log of this denominator minus 0.5 times whatever term I've got over here. So this is just my log Gaussian for one observation, and I'm going to be summing it over all of my observations. And I can just maximize this equation over here, which is the log Gaussian for my entire training data. And maximizing that with respect to theta and d will give me my estimate for the NLGM. Is this making sense? Guys? Raise your hands if it is. So I'm not going to explain the loss function. That's a waste of time. I'm expecting you guys to go back and look at the slides for to understand this function. But what we are saying is that if I gave you the Z, then it's going to be easy enough for me to compute the log likelihood of my training data. And although I can't maximize it using a simple closed form solution, this is my loss. I can use backprop. I can estimate both theta and d, and I will get a solution. Yeah. The problem here is Z is not given. So what do you think we will do now? Anybody? EM. So can you expand on that? What will we do for Z?
So we fill in the missing Z by drawing from.
We're going to. We're going to complete the Z. Correct. Yes. You could estimate the model parameters if Z were known for every data observation. Unfortunately, we don't know Z, so we're going to complete the data. And the way we complete the data is, I'm going to, one option is I can try to compute P of Z given X and try to come up with a closed form solution. And, try to complete the data in every possible way and try to estimate parameters. But in this ugly function, that is not going to be feasible. So we are going to be using this second option, where we will draw samples from P of Z given X and use the drawn samples for each of these vectors. I'm going to use the drawn samples to complete the data. And I will use this completed data to estimate my model parameters. That making sense? Guys? Is this making sense? Raise your hands. Yeah. Okay, so that's what we're going to try to do. Now, so in general, using every possible value is to be preferred over sampling. If the farmer produces a tractable closed form solution, otherwise we must use the sampling version. That's what we will do. So here's the problem. P of Z given X is what we want to sample from, right? P of Z given X is P of X given z times p of z divided by p of x. This is the base rule that we actually use to compute p of z given x. And the problem is that this denominator term, this is going to be the integral of p of z given x, p of x, wait, p of x given z, p of z dz, right? That's going to be p of x. And if you write out the integral, that integral is hideous. It's this integral. It includes a Gaussian whose mean is itself a very ugly nonlinear function. This cannot be computed. So because this cannot be computed, although I can compute p of x given z and p of z, I cannot compute the denominator, so I cannot compute p of z given x. And because I cannot compute p of z given x, I cannot sample from it. And so we're going to do one step more. What we will do is approximate p of z given x. And we're going to approximate p of z given x with some function q of z, which is a function of both z and x. And this function is going to be a Gaussian. The Gaussian is going to have a mean, which is very specific to x, and a variance, which is very specific to x. This is just an approximation. We're going to be using a Gaussian because we know how to deal with Gaussians, right? And so we're going to assume that q of z semicolon x is a Gaussian with a mean which is a function of x and a variance which is also a function of x. And now, what kind of function of x is the mean and the variance? These two are parametric functions of x with parameters psi, okay, the phi. And we try to learn these parametric functions such that this q of z comma x with mean mu x and variance sigma x is as close as possible to p of z given x. And once we do that, I'm going to use q of z comma x as my proxy for p of z given x for sampling. So is this making sense, everybody? Okay. So that's what we're going to do. Okay. And so here's what we're going to do. The overall solution is I'm trying to estimate f. This is what I'm trying to estimate. I'm trying to estimate d. But in order to estimate d, I need to be able to fill in these z values from the posterior distribution. But the posterior distribution is itself being approximated. So I also have to estimate the parameters of mu and sigma, correct? So I'm going to initialize my f. And then iteratively, I'm going to estimate the mu and the sigma to give me the best QZX, where by best I mean the QZX that approximates P of Z given X most closely. And then once I've estimated mu and sigma, I've got this distribution. I'm going to use it to complete the data by filling in Z. And then once I fill in Z, we've seen how using the complete data, we can re-estimate, re-estimate theta, right? So is this making sense, this process? Yes or no, guys? Okay, so that's what we're going to do, right? And so here is the complete pipeline. This is going to take 10 minutes more. I'm going to initialize theta, which is my actual generative model, right? This is my generative model. But I'm also going to initialize the phi's, which are the parameters that allow me to approximate P of Z given X. And now, when I've sampled these guys, when I've initialized these guys, I can use these initial values to generate samples of Z. And now that I've sampled GZ, I've completed the data. From this completed data, I can re-estimate theta. And then from the same completed data, right, I can backpropagate errors and also re-estimate these guys. So that is the process that we're going to do. So let's take a look at it. to take a closer look. I'm going to initialize theta and phi. This is theta and this is phi. And now that I've got a phi, my function q is a Gaussian. For every input, every training input x in my data set, I'm going to get a mean and a variance that's specific to that x. So because, you know, q of z comma x has got to be a function of x in order for it to compute p of z given x, right? So for every x, I'm going to get a very specific Gaussian, and I'm going to sample one or more z values from this Gaussian. And how do I do this? Now, this is your standard reparameterization trick that you'll keep hearing about when you're talking of variational autoencoders. Anytime I want to sample from a Gaussian with mean mu and variance sigma, what I will do is to sample from a zero mean unit variance Gaussian. And this is going to give me some initial value, you know, let me call this alpha, let me call this y. And then I will multiply y by sigma inverse and add mu. And when I do this, this is going to give me a sample from n mu sigma. So so sampling from this Gaussian basically means that I'm going to draw one or more samples from a standard Gaussian, which is zero mean unit variance. Then I'm going to multiply it by the standard, the square root of the variance, and then I'm going to add the mean. So this is how I am generating the sample. So this epsilon came from 0, pi. This is my variance, and this is my mean. And that's how I'm generating my z. So is this making sense to you guys? Inverse, okay. Has it got to be? No, it's not an inverse. There's actually a 0.5. That's a plus 0.5. Thanks, Danish. You're right. Just a square root of x. The square root. You're absolutely right. Okay. So now the point is, because z is now an explicit function of mu and sigma. Therefore, z is a function of phi. And because z is a function of phi, I can compute the derivative of z with respect to phi. It's very simply the derivative of z with respect to mu, which is 1, times the derivative of mu with respect to phi, plus the epsilon times the derivative of the square root of sigma with respect to phi. So this allows me, now if this term and this term are actually neural network functions, neural networks, then the derivative of mu with respect to phi and the derivative of the square root of sigma with respect to phi both can be computed using backplot. And so I will get a derivative of z with respect to the parameters of the networks that compute the estimated mean and variance. And this is going to be very specific to the input x, right? Now, because these guys are functions of x. So we know how to compute the derivative of z with respect to phi. And so at this point, we know how to sample. Let's see how we can re-estimate theta from the complete data. And we've already got our z's, right? We've sampled. So if I've got the z and if I've got the x, we've already seen how to compose a loss function that can be maximized with respect to theta and d. So we have a loss function that can be minimized to estimate both theta and d. So the second step is handled. I'm not going over this fine detail, for that you'll have to look over the slides. So this has been handled. This has been handled. The third one is, now how do I estimate phi from my data, right? And again, we want this q of zx, which is this Gaussian, we want it to approximate p of z given x as closely as possible. So I'm going to estimate these phi's to minimize the error between QZX and P of Z given X. The first thing I will do is I will define a divergence between these two guys. Specifically, I'm going to use the Kullback-Leibler divergence. And then once I have the Kullback-Leibler divergence, I have the Kullback-Leibler divergence between Q and P, which is the expectation over all Z's drawn from Q. Remember, the KL between any PQ is summation over Q log P over Q, right? Q over P. So that's the formula that I'm using. So this is the expectation over all Z's drawn from Q of log Q over P. The variable, remember, is Z, right? And I can write this as expectation over Z drawn from Q of log Q minus expectation over Z drawn from Q of log P of Z given X. I can write P of Z given X in this manner, which is P of Z times P of X given Z divided by P of X. And if I expand out the log, I still get this first term. And then this second term is the log of this first guy. This third term is the log of the second guy. And this last term is the log of P of X. Now here is the magical thing. Log of P of X is not a function of phi. It's just the natural probability distribution of the data. And so this one, log of P of X is a function of theta. It's not a function of phi, because this is the probability distribution of the output of the generative model. So if I'm trying to minimize the Kullback-Leibler divergence, I can ignore this guy. And so magically, this horrible term that we had to deal with, which was the probability of X itself, disappeared. Secondly, if I look at these two terms together, the expectation of over Z drawn from Q of log Q minus log of PZ is simply the Kullback-Leibler divergence between Q of Z given X, Z comma X, and P of Z. And P of Z, this is the a priori probability of Z. This is the input that's going to the generative model. So this P of Z is just a standard zero mean unit variance Gaussian. That's how we defined it, right? And so this first term becomes the Kullback-Leibler divergence between QZ, Z comma X, and P of Z. And then we have this second term, which is simply the log probability of so this should have been Z, which is this term. And this guy, which is P of X given Z, this is a function of theta. Remember, P of X given Z is a Gaussian with whose mean was the decoder function computed at the specific Z. So that third term is this one. So the overall objective function that you're going to get ends up being this very small. Actually, this can be removed, right? This very small objective function, which is the Kullback-Leibler divergence between Q of Z comma X and the a priori probability of Z, and the expectation over Z drawn from Q of the log of P of X given Z. I don't expect you to understand all of this. The math is on the slides. Again, my intention is just to try to get the concept across. I expect that you will go over the slides. And so I'll skip the more detailed math over here. And that finally gives us the complete training process. I'm going to initialize my parameters. I'm going to sample my Z's using my initial phi. Then we know how to compute a loss function for this guy. So I can re-estimate my theta using this loss function. Then I can, we sort of worked out how to compute a loss function for the phi's over here. Again, look over the slides. And so then we can update the phi's using the second loss function. So this is estimating the nonlinear transform of the NLGN. This is estimating the function that approximates the a posteriori probability P of Z given X. And instead of having them in two separate steps, I can combine the two loss functions into one, just add them up and say simultaneously, minimize over the functions of my generative model, the variance of the noise, and the parameters of the model that actually compute this mean and the variance. And this is going to be a very simple iterative process. The loss function is very clearly defined. And so you can use standard gradient descent to optimize this loss function. So the standard approach is going to be you initialize your model parameters. Then for each training instance, you can sample one or more Z's. And then for the Z's that you've got, you can compute this loss function. And you can compute the gradients of the loss function with respect to theta and phi and the noise D, and use those within your standard stochastic gradient descent update to update your model. So, and once you've updated the model, the decoder is just the generative model. So the whole thing is called a variational autoencoder, because if you look at the model from here, from this perspective, X goes in, you're sampling some Z, and you're expecting it to generate X again. So it looks like you're encoding an X term X. So it's called a variational autoencoder. This is the encoder, and this is the decoder. And it's variational because we use the calculus of variations again and again. We use it when we're performing EM, and we use it when we approximate P of Z given X using this function Q. So where are the neural networks in all of this? This F is a neural network. The functions that compute these guys are also neural networks. And so the entire thing is just all neural networks. So this is the variational algorithm. Give me a second. The decoder here is the actual generative model, and the encoder is primarily needed only for training. And it can also be used to generate the approximate latent space representations for any given input. Okay. So we've sort of gone over the math of VAEs. What's it useful for? So VAEs are strictly generative models. They can be used to generate samples of data, but you cannot use it to compute the probability of a data, because as we saw earlier, P of X is not tractable. And so if I give you an X and ask you what is the probability of this X, it's impossible to compute this guy. So you can't compute probabilities, but you can generate samples of data. And yet they are very highly effective as generators. They can learn very complex distributions. So here, for example, this one was a VAE trained on MNIST. And then if you just take this generative model and feed it random values of Z drawn from a standard Gaussian, if you view what the X looks like, you see that it actually ends up generating things that look a lot like digits. In this case, there was a VAE trained from faces. And then when you feed the VAE random Gaussian noise, the generative portion of the VAE random Gaussian noise, it actually ends up generating outputs that look like faces. So this guy has clearly learned to generate digits, and this guy has clearly learned to generate faces. And then there's this other thing. Now, I can take, so you have this X, you compute a Q, and you have the mu X and the sigma X that goes in. From this, you draw a Z, and then you put this through F, and you estimate an X again, right? Suppose I did this on an X1, and I suppose I did it on X2. Two different inputs. So this is going to be mu X1 and sigma X1, and have the corresponding mean and variance for the second term as well, besides second input as well. Now, if I feed just this mean into this Gaussian, into this decoder, this output is going to look a whole lot like this guy. If I feed the mean of Q over here into this decoder, this output is going to look a whole lot like this guy. And these two are in the latent space. So if I draw a line between these two means and sample different values of the mean of the latent variable along this line and pass those values through the decoder, what do you get? It turns out it actually learns the structure of the data. So in this example, you know, one of the inputs was this face, the second input was this face. And then if you took a value of Z, which was in between these two means and passed it through the decoder, it actually outputs a face which is halfway between these two guys. Similarly over here, one input was this face, the other was this one. And if you feed the decoder a Z value that's halfway between these two guys, it generates the one in the middle. So it actually learns the underlying structure in the data in a very nice and smooth manner. And varying Z continuously in different directions can result in different plausible variations in the drawn output. So I'm sort of terminating abruptly because I've used too much of your time. But then VAEs are simple nonlinear extensions of linear Gaussian models. They're excellent generative models for the distribution of data. And you have various extensions like conditional VAEs, which model conditional distributions. And you have other extensions where the latent variable distribution, P of Z, you can use something besides Gaussians. You can use other kinds of distributions and you get other variants of VAEs. In all cases, the arithmetic for learning is very simple to what we saw over here, which is given, and when you're trying to learn the model, we try to complete the data, the Z value for the X, and then using the complete data, learning the decoder, learning the generative portion of the model is very straightforward. The real challenge comes in trying to estimate the a posteriori probability of the latent variable, for which you come up with a model that approximates the posterior distribution. And so that must be learned as well. And that ends up, the math over there is just marginally more tricky. If you go over the slides, you will see that it's not that hard. And once you set this problem up, you have different ways of varying the distribution for Z, the a priori distribution for Z, the structure of your F and the Q, and you come up with different kinds of models. So anyway, I'll stop right here. I've run out of time. I apologize for taking too much of your time. I'll stop the recording.